Good weekend. All right, today we'll review and I will emphasize more about Bernoullis Principle that you hopefully read about in the text. We will go back over chapter 13 and 14, liquids and gases. Remind you, your exam on this then is Wednesday. I also want a friendly reminder, because it's been a while, your superhero paper. All the instructions are online in WebAssign under the resources. Everything and how I'm going to grade it and what I expect and what you need, how to type it up and how many words it needs to be and when it's due, and even an example paper from a past student that was agreed to let me post it. April 1st. It's due up until April 1st. You can turn it in anytime, according to the instructions. I'm just friendly reminder. So you have about a month. Because, well, frankly, you have no excuse to turn that one in late. I understand most of you will probably wait till the last moment to do it, but that's why I'm giving you another friendly reminder, so you remember that you still have a paper. My main impetus for, as stated in the instructions, or the syllabus, for having you write a paper in a physics class is because I honestly believe the best way for you to understand physics is to try to explain it to someone else. So if you ever tried to help somebody else with their homework, or tried to explain any of this to your roommates or your mother, I don't know if you have, it's harder. And so I think you kind of solidify in your mind really what you're thinking when you actually try to regurgitate it. It's one reason taking notes is so helpful. You take it in, it makes sense, but can you write it back down in your own words? Anyway, I thought the superhero paper is a fun way to do it. How many have not read the instructions yet at all? Be honest. Just figured you'd wait and, okay. Well, may I suggest you at least read it so you know what's expected? Because the gist is you design your own superhero and you create one with a superpower. That superpower can either abide by the laws of physics or not. But you have to justify why. The point is you have to show me you understand some law of physics. But it's kind of fun that way. And you can pick any principle of physics. Ones we've covered in class or not. So that way you might have it in your head. If something pops up, you'll know, oh yeah, I want to write it on that. So be reviewing those since there's only a month left. If you got any questions, let me know. The last thing I crammed in the lecture last time was Bernoullis Principle, the demonstration where I had a big thing over here with some green fluid, and I blew air into it. And it went through this pipe, and then the pipe narrowed, and then it got bigger again. And the point of this is to show Bernoullis Principle. And that is that when fluid, like air or water, is moving faster, there's an associated decrease in internal pressure. I was trying to show you that. We had a tube here, and a tube here, and a tube here. And they were full of water. When I turned the air on, because air is moving now, you can get another change in pressure. That's the gist of Bernoullis Principle. Up till now, we've kind of been static. But when air is moving, the deflection of the air, as it gets bent and whatnot, that requires forces and things. And so things happen, and pressure can change. Here, the water went up. It rose up, showing that there was less pressure in this region. So the other areas had a larger pressure relative to this spot, and it pushed the water up. The column of water was higher here. That creates a bigger pressure head down here. That's what the higher pressure was supporting. But again, when fluid flows, and it gets constricted into a narrower region, it has an associated decrease in pressure. That's Bernoulli's principle. Now, it has lots of stipulations. It depends on whether it's laminar flow instead of turbulent, smooth versus choppy. It has to be in an enclosed and only along the streamlines, but I won't bore you with that stuff. The gist is, here the pressure is greater along this streamline. These blue things are called streamlines. You just imagine this piece of air, a little section of it, and it travels along. One that goes along here is feeling a certain pressure, and when it gets in here, it speeds up and exerts less pressure. And then it slows back down and can exert more pressure. One up following the streamline up here, same idea. It's going a certain speed at a certain pressure, and it gets deflected into the narrow region. So it speeds up and has less pressure it can exert. So there's less pressure in this region, and then back to high pressure and slower speed. Does that make sense? That's really the gist of Bernoulli's principle, and I was trying to show you there at the end. Now, one way to help you remember, it kind of bothered me. Why does it speed up? Flow rate. There's something your book doesn't give you, but it helps me understand it, so I'll share it with you. Conceptually, there's something called the continuity equation. And it says that the area, the cross-sectional area of the pipe or tube or whatever, times the volume of the fluid going by stays constant. Okay, so what's that mean? That means, think of water flowing through a pipe. The same amount of water gets through this part of the pipe as it does this part and as this part. That makes sense, right? In order to get through this narrower region, it must speed up to keep the same flow rate. Just because you squeeze your garden hose a little bit doesn't mean that the same amount of water doesn't come out. It just ends up going faster. You've probably even done that at the end of the tube. You put your the hose, you put your thumb over the end, and you kind of narrow the space coming out. And what's the water do? It shoots out faster. That's essentially Bernoulli's principle. And it's just maintaining the continuity equation. So more mathematically, this area here, we could say is A1. Has a certain volume. Here you have A2, different volume. They stay the same. So it's one of these games. On the left, you have a big I fell into my own trap. Well, I'm wrong. That's velocity. Sorry. We're talking about speed here, and I start drawing volume up there. Sorry. Back up. Area times the speed that it's going. That's the flow rate. The area takes care of the size. I don't need the volume. I'm sorry. I was wrong. So, if the side area on the left is bigger, it's going slower. The area in the middle is smaller, so it goes faster to keep the flow rate the same. That kind of helps me remember, oh yeah, if it's getting narrow-necked, it's going to speed up. And then we go back to Bernoulli's principle and say, if it's speeding up, it must also have a less internal pressure. Bernoulli's principle is, in essence, conservation of energy. Get my sheet here. It says, this is in a footnote of your book too, and I'm not going to make you do calculations with this equation, but you can understand it. And that's velocity. 1/2 times the density velocity squared. This looks kind of like kinetic energy, doesn't it? But it has density instead of mass. And this looks like gravitational potential energy, doesn't it? But again, it's got density instead of mass. And this, if you account for the volume thing, would be like work. I won't do that with you, but yeah, if you divide by V and convert those back to mass, you get that the energy is conserved, the total energy. So the games a lot of scientists play is that, if it's moving, more energy is associated with kinetic energy, the energy associated with motion. So it exerts less pressure. That's what we just said. Also with height, we've already seen this. If something has a bigger column, you're farther down, deeper, you get more pressure, don't you? But as you go up and increase the H, more of your energy of that parcel of water has less pressure. It has more gravitational potential energy at the expense of having less pressure because we're higher up now to keep energy conserved. Does that make sense? Let's see. So say you're in a water tower. Woo! Holding your water up there. Up here, the pressure isn't as great as it is down there because of that height. Remember, we had pressure that is pressure. The more on top of you, the greater the pressure. So as you rise up to here, the total energy is the same. It's just more in gravitational potential energy. And then as we did, say you poke a hole here and it shoots out, right? That pressure, the energy associated with work done to shoot it out, is converted to kinetic energy and now has energy associated with motion. If water was just going through a tube like this, and it drops down, this would be under greater pressure than up here because some of the gravitational potential energy got converted to work done on the water. And if this changes size, then it speeds up because more of the energy goes into kinetic energy and it has less pressure. So, when you deflect things, let's do this one. This is a piece of styrofoam in a clear tube. When you blow over the top of something, like your book explained, it deflects the air. It narrows it. It kind of restricts it. It's similar to that picture up top. And when it narrows, the pressure drops in that region. If the pressure drops here, does the pressure drop down here? No, why should it? What's this pressure at? What do we call the pressure in the room? Atmospheric pressure. And what causes atmospheric pressure? The what? What about the atmosphere? Yeah. The weight of the air. Yeah, there's lots of air and it weighs stuff. It's pushing on it. So it's pushing here, and it's pushing there, and it's pushing here right now. They're all equal. But by blowing over the top, it deflects the air, and it speeds up. And as Bernoulli discovered and explained to us that when it speeds up, more energy is in kinetic energy, so it has less pressure. And then now there's a difference in pressure on the two sides here. And the air in the room, the greater pressure lifts it up. That's what we call lift. That's how airplane wings work. If the airplane's coming through the air, then the air is coming at it, and the air gets deflected over the top. This constricts it more. You can think of it as narrowing it, getting in its way. So the air is moving a little faster above an airplane wing than it is below. So where's the pressure greater? Below the wing. Yeah, there's a difference in pressure from bottom to top, and that provides lift. How much lift do you need to hold up a 100-ton airplane? 100 tons, yeah. So you can get a difference in pressure. And remember, pressure is force over area. That's what you need 100 tons of that, right? So if you adjust the airplane's wing area, you know how much pressure difference you need between bottom and top. Yeah. I'm glad you asked. I'll come to it. You know how much pressure you need. And according to Bernoulli's equation, if you need that change in pressure, you know how fast you got to be going. So if it flies upside down, what the heck's it doing? There's another way to think of lift. This is Bernoullis Principle to match with the fluids we've been studying. But you can understand lift with Newton's laws. Think of it this way. As the airplane comes in, what's it do to the air when it hits it? It exerts a force on it. And the bottom side, generally, it hits it and deflects it down. So the airplane wing pushes the air down. What's the air then do? Push the wing up. So who cares if it's like this or like this? If it's coming at it, it can still deflect air down. The top is curved. Some air will go over the top. But when it curves, there's another thing. It kind of sticks to the surface a little. And lo and behold, the air on the top gets deflected down also. Because it's coming along. It comes over here, and it tries to follow the surface. It deflects it. And so the air underneath and the air on the top are both deflected down, both of which create lift. So when an airplane is upside down, this curvature is now trying to deflect it up. So its angle of attack has to be even larger for an airplane flying upside down, and or it has to go faster. So it is more difficult, but it's still possible, as long as you have a net lift. But yeah, I like that. Newton's third law comes back into play. Some other fun ways to do it. Here you go. Some peanut butter M&Ms. Take one and pass it around if you'd like, but don't eat it yet. I'm going to try an experiment. I practiced. I figured if you can do it, it'll be great. If not, well, you get an M&M. And hopefully there's enough. If not, I got another bag. But you can blow on things like this. And I tried it with the peanut M&M. It works. The air is deflected around the sphere, just like I can do with this big beach ball. The air hits the surface, and just like the top of the tube or an airplane wing, it's deflected. It's constricted. It speeds up, and the pressure's less there. And the higher pressure in the atmosphere keeps the ball in the stream. You can think of it as it starts to want to go out, the higher pressure pushes it back in. It's lift, kind of like sideways. It'll hold this ball up too. So what do you think will happen now when I turn it on? Goes up? I love that one. Just another example. When it's in here, the air is coming out. And what's it doing? It's expanding to a bigger area, isn't it? So it's like our tube up there. It goes from a small area to a big area. And so the pressure changes because the speed changes. Or you can think of it right in here, it's constricted, it's narrow. So it's going faster here with less pressure. And there's greater pressure out here. And that difference on the two sides provides lift. And it keeps it in there. So even when I turn it upside down, it was enough lift, difference in pressure, to hold up the weight of the ball. Does that make sense? So if we're about halfway through, with your peanut M&M, you can be practicing while I'm lecturing if you want. It took me about 5 minutes the first time. So suggestions. Hold it about, get your head tipped back so it's vertical. Hold the M&M about an inch away from your mouth. And it's crucial to try to blow in a nice, steady, even blow. And don't try to blow as hard as you can, like, then you run out of air. You kind of have to hold it back and purse your lips. Because do this. Not only do you knock out your neighbor because of halitosis and bad breath, but it's warmer because you have a big area. Now pierce your lips and blow. It's cooler. It's moving faster because of Bernoullis Principle. Remember, when you constrict the area? Anyway, so that'll allow the air to be moving faster, and there'll be more deflection and more lift. So you can just try it. True, a ping pong ball works better than the peanut M&M, but give it a go. And when you get frustrated, eat it. Okay, that's what I wanted to tell you about Bernoullis Principle. Some other examples were in your homework, but I want to turn it over to you. I want to see if you guys have questions first about all this stuff. Let me cover what you guys want. If not, I got more, don't worry. So, questions for the exam. And don't give up. Like I said, it took me, I could do the ping pong ball for years, and it still took me about 5 minutes first time to get the peanut M&M. So give it a go. No, any questions? How about on the homework? Anything people got bothered with? Things in the text you didn't understand? Past lectures? You guys are all confident? All right, raise your hand if you get one, okay? Then I'll carry on with some review. Key points was this. What is pressure? We dealt with forces up till now and moved them around, but it's important on the area that force acts, because that creates a different amount of pressure. Remember, this is like snowshoes, big area, less pressure, versus high heels. Same force over a small area can create a lot of pressure. Or the hovercraft. If you rearrange this, we didn't have much pressure with the leaf blower, but if you spread it over a big enough area, you can create enough force to hold up an entire person with just a leaf blower. So those relationships. And then that led to Pascal's principle a little later. And Pascal told us that in an enclosed container, the pressure is equally distributed everywhere. We saw that with hydraulic lifts. If you push over here, then that pressure is transmitted equally over here. So if this is a fluid, and you push on one side, it'll be transmitted over here at the same pressure, Or vice versa, you push on this side. It's transmitted over here. And what that allows us to do, it's not a simple machine, but it's a machine. And so you get this concept on both sides. If the pressure is the same in the middle, you can multiply your force. Remember, if you push down over here, let's say, with a little force, well, that's a smaller area. That's okay. The ratio is some pressure. That pressure can equate over here because it's a much bigger area. You can get a lot bigger force out. And so you can multiply the force. You can't lift a car by yourself, but if you build a hydraulic system, you can push over here and lift the car. What are we not multiplying? Work, energy. Yeah, energy is conserved. So which end would have to move further in that example? Well, raise your hand. Who thinks this side would have to move further? Who thinks this side? And most of you aren't voting. Well, work is force times distance, right? This side has a little force, so he's going to have to move a lot further to create the same amount of work and energy on this end as he's going to get out over here. Energy in has to equal energy out, so the same work here has to be done there. So this guy won't end up being moved as far. That's like our lever. If you got some mass, remember you can push down over here. It'll be easier to lift something heavy. But this is only going to move all right. When you do that, can you see that you would have to tip this further? I thought if I drew it, it'd be more explicit, but it looks like it wasn't as conspicuous as I was hoping. And this guy would move a little less to keep the work the same. Or that pulley example, that was better. Remember we had the tug of war with the pulley? And the female was pulled a lot further, but with less force. But she was able to pull the two guys together. They didn't move very far, but it was the same amount of energy. So back to Pascal's principle. This guy will end up moving further because you're not pushing as hard. So you got to move further to have the same amount of work if you're going to be lifting a car over here. We did already discussed pressure increase with depth. So as you dive deeper and deeper into the ocean, the pressure increases on you. And it's not dependent on volume, right? It doesn't matter how wide the container is above you. It's just what's above you. What if you replace the water above you with syrup? What happens to the pressure? Why does it go up? Yeah, more dense. So that would exert more pressure too. What if we went to Jupiter and had the same column of water on us, or dove to the same depth if there was an ocean there and you could survive? What do you think would happen? The pressure would be greater because, if you didn't know, gravity on Jupiter is a lot bigger. On the moon, if there was an ocean and you dove down the same depth, it'd be less pressure because gravity on the moon is less. Good, good. We already hit on this one too. Whoops. But density, mass over volume, the ratio, both matter there. So if you take a balloon and squash it, what happens to its density? I heard the answer, but I was surprised less of you seemed confident. You take a balloon and shrink it, squish it. What happens to its density? Yeah, it goes up because its volume decreased, and that would increase the density. Which happens to a balloon? That's right, I discussed that. As the balloon, if you take a balloon, you know, you should YouTube picture, not YouTube, but Google pictures. I saw it out there. A styrofoam cup is pretty much a bunch of air pockets. And I've seen pictures of scuba divers that took styrofoam cups down really deep. And what happens to the pressure as you go down? Increases. So what's that do to the air pockets in the styrofoam? Makes it smaller. Yeah, it crushes the cup, but it doesn't smush it. You know, these little pockets. It goes from like that to because as the pressure goes down, it shrinks. Yes?
They did that with Alvin when they dove down, I don't know how far into some trench or something like that, and they had a styrofoam head, and they did makeup all over it and everything, and it shrunk down from like normal size head to about like that big.
What was the head made out of?
Styrofoam.
Oh, made a head out of styrofoam, took it down, it shrunk. What impresses me is that the scale kind of stays. But it should. Think about this. The pressure here in air is the same as there, isn't it? Air's inside the cup and outside. In air. So as you go down, you know, you say you're hundreds of feet down, the pressure on a little cup is almost, well, it is the same here as it is here, as it is over here and here, because they're at the same depth. So inside and outside the cup are the same. So instead of squashing the thing, it just kind of shrinks it, because each of those little bubbles are smaller. And that was Boyle's law. I mentioned it. I didn't write it on the board. It's in the text. But that's what that said. This one is volume. That ratio, pressure and volume, stays constant. That means if you have P1, V1 in this case, it's got to equal P2, V2 in this case. Again, it comes from energy must be conserved. We saw that with the, I just didn't connect it as well as I'd hoped to the bell jar. When you decreased the pressure, the volume increased. Same with the shaving cream. You see it too when you put leftovers in your refrigerator. We're going to get into that in the next chapters with thermodynamics, but you like seal off your hot leftovers in Tupperware and you put it into the fridge and it cools off. What I don't expect you to know yet is that when things cool, the pressure decreases because that humid moisture, whatever, condenses and takes up less space. Well, if the pressure decreases on the thing, it can't push out as much, and the volume changes. That's not a perfect example of Boyle's law, but I thought I'd at least, as my teaser for next time, you know, with thermodynamics, something for you to think about. Then we had sinking and floating with buoyancy. That was the last one, concept. So, I wanted to write it this way. Float, sink. Okay, tell me a condition. Why would something float? So the density of the object is less dense than the fluid. Yeah, so the opposite, it would sink. So if you change either of those, it can affect whether something sinks or floats. So if you like transfer it in from fresh water to salt water, you just change the density of the fluid. Something might sink that used to float. You can do that sometimes with things. If they're just floating underwater, add a bunch of salt to it. No, other way around. If, say, it's just sinks. Yeah, if it just sinks, that means the density of the object is a little bit greater than the fluid, right? Well, what if you increase the density of the fluid by adding salt? If you add enough, eventually, the thing could rise back up. Yeah?
I thought I heard about that there were certain depths in the ocean, there are like cold seas, something like that, where it's super dense salt water, like more dense water above it, and then like submersibles can't go into it because it's so dense.
Yeah, there are layers of different density water in the ocean. Just like there's different densities of air layers. Here, perfect, all our pollution, inversions, hot air is less dense than cold air. So it rises up, it floats. But what if you get it trapped? It sits there and collects pollution until a storm comes and change in pressure blows it out.
Isn't it also due to pressure is also with that deep in the ocean, it just keeps it there in like a super cool.
Yeah, the depth of the ocean does affect how why it doesn't move, yeah. Because just like the wind and the air in our atmosphere, the reason we get wind is differences in pressure. It makes a fluid move. And it's the same thing with any fluid in the ocean currents. Absolutely. Good connection. What's another way, though, you can determine whether something floats or sinks? Displacement of fluid. Yeah, which gets us to buoyant force, doesn't it? So let's take our mass. Whoop. It has a certain weight. What would make it float? An equal? Greater, yeah. I guess I got to draw it up there. And we call that the buoyant force. If the buoyant force is larger than its weight, it'll rise up. And if it's less, it'll sink. It'll go down. What if they are equal? It just sits there. It's called neutrally buoyant, as your text explained. I love doing that with helium balloons. Next time somebody gives you one for your birthday, right? Weight it down with like tape or paper clips until it's just floating, like hovering there. That's when you know that these two are exactly equal. It's fun because then as the helium kind of leaks out or the air leaks in and changes the density of the balloon and it wants to sink, you can trim a little tape off or remove some paper clips and they'll be equal again. It's fun watching it just float around the house too. My daughter loves it because the currents in your room will make it move. And over here the air might be a little warmer. If the air's warmer, what's that do to the air's density? It's a little less. So if the thing is normally floating and we just made the fluid a little less, it might start to sink, and vice versa. So you can kind of see pockets of warm and cold air in your room too. If you have it just floating, kind of push it over here and it goes up. Push it over there and it kind of goes down. Anyway. Right. And somebody mentioned that the buoyant force is based on how much water you displace, fluid. The weight of the displaced fluid. So if you displace more fluid, it's going to weigh more and you get a bigger buoyant force. But remember, just because something's underwater, that means it has a buoyant force, right? Because it's displacing water. But that doesn't, tell us whether it sinks or floats. You got to look either at its density or these two forces. Something that's huge volume-wise, but on the bottom of the ocean, has a huge buoyant force, right? So what do you know about its mass? It's got to be pretty great because that huge buoyant force isn't overcoming its weight. But something really small, like a cork, can float on the top. It doesn't displace much water, but it doesn't need to because it doesn't weigh that much. I'm sure you've all played with suction cups, and the textbook has some great examples on this that I left to it. But when you take some suction cups and you push it against something, in this case each other, what's it do to the air in between them? It does compress it, and if you didn't realize, some of the air leaks out. So basically there's less air in between the two cups. So there's less pressure between the two cups. But we haven't changed the pressure out here, have we? So what's holding this up? Atmospheric pressure. The air on this side is certain pressure over a certain area, right? Creates a force. And you get a similar force on this side. And that force is holding them together so much that you can't pull. We can do it. Come on. All right. I'm ready. Proves our point. That's how suction cups work. This is just a piece of rubber. It's flat. It's not even curved. But when I plop it on the stool, yeah.
Why is suction cup so strong if it's only 15 pounds per square inch?
Great question. Great question. Why is it so strong when it's such a small area, it looks like? I'll answer that even better after this one. So it's on there. I can lift up the whole stool. Again, when it goes down, it squishes some of the air out from in between the rubber and the stool. And so the air in the room has greater pressure, and it's pushing on the top and the bottom, squeezing it together over an area. And that's enough force to lift the weight of the stool. If you let some air back in, then the pressure equalizes. There's no difference in pressure. You don't get a lifting force. So let's see, one of these. You're pulling apart because the air is pushing in. So the thing is, the difference in pressure from outside to inside. The inside's less pressure, the outside's greater pressure. For simplicity's sake, let's say we could get all the air out in between. Then what would be the difference in pressure? It'd be equal to right, 1 atmosphere, 14.7 pounds per square inch. Or in Utah, it's closer to 12.5. Did you get the idea? And then that pressure is applied over an area. So you'd figure out this guy's area. And you'd get the force from just one side. Then you double it because the same thing's happening over here. And that's the total force you have to overcome to pull it apart. Plug in those numbers and you can see it's pretty strong. The Magdeburg hemispheres, Otto von Urich, who was a mayor of Magdeburg, if you read the text, he made 2 hemispheres and he evacuated the air out in between. And he had teams of horses that couldn't pull them apart because the air was holding them together with such force. They were obviously bigger than these. But yeah, you increase that area or drop the pressure even further, you can get a huge amount of work to do. It's pretty impressive. So one of my all-time favorite pressure demos. Oh wait, is anybody able to do it? I watched you for a while, but you guys... Nobody was able to do it? Well, you can come try another one later. Oh, you got a left arm? Pass them around. Who wants one? Merry Christmas. So I'm going to take this ping pong ball and roll it down this pipe. Boink. It's on the other end now. I got some packing tape. I'm going to seal this end off. I want a good seal. Some pop cans over here. And then I'm going to seal off the other end as well. Good seal. All right. Now I have a vacuum pump down here, and I'm going to start evacuating the air. So the ping pong ball is right here. What's in front of it? Yeah, it was air, a lot less air. I'm pulling most of it out. What I'm going to do is rupture the tape on this end. Which side of the tape is the pressure greater? This side or this? The outside, atmospheric pressure. A difference in pressure. For argument's sake, say I pull all the air out. It's a perfect vacuum, which isn't true, but it's close in this case. So 1 atmospheric pressure, 15 pounds on every square inch. We'll figure out the square inches here, and that's the force exerted on the ball. And you know a force on a ball makes it accelerate. You guys ready? 1, 2, 3. Whoop, missed. Ooh, that's a good one. Here's can number 1. It busted right through it. Can number 2. And didn't make it through can number 3, but it dented it and ripped it. That's a good thing, though, because we didn't want shrapnel going over there. And let's see. Here's what's left of the ping pong ball. I've measured this. The ball comes out of here at about 70, well, that one was probably about 75% the speed of sound. That's over 500 miles an hour, just from a difference in air pressure. Over an area, accelerating little inertia, so it gets cruising. That's fun. I like that. Any last minute questions for you guys? May I encourage you to review your homework. And if there's any questions I guess you can think of before test, email me or call me.